phone! Casey, your phone! Turn it off! Come on!
I mean, the premise is you can't have anything electronic. So he destroys the guy's phone, but he's still got a bloody torch in his hand. Like, that's powered by batteries. That's electronic. Oh, Jesus Christ. Moonfall is Roland Emmerich's latest sci-fi disaster movie, and in it, the moon starts to fall to Earth, causing chaos and destruction. Even in that one sentence, there is so much to unpack, and I think this is why so many of you requested that I watch and react to this film to chat about which bits are backed up by science and which bits are firmly rooted in the fiction part of science fiction. This is not a serious scientific review, it's just a bit of fun watching a sci-fi disaster film that hopefully we'll all learn something along the way. So without any further ado, let's dive into things. Let's press play.
But don't even get me started on eclipses. They're only possible because the moon is exactly 400 times smaller than the sun and exactly 400 times closer to the Earth. Anyone know how that happened?
I mean, yeah, it's just coincidence, right? The moon didn't used to be that distance from Earth. So the moon was actually formed when another sort of protoplanet in the early days of the solar system collided with Earth and essentially was vaporized. It put a load of like junk in orbit around Earth, which slowly coalesced and formed the moon much closer in to Earth. And essentially what's been happening since then is that the moon has been slowly moving away from the Earth all of the time as the two essentially exchange energy, and the Earth essentially slows down in the rate that it spins at. That impact spun up the Earth so that a day would only have been a couple of hours soon after the impact happened. And essentially, as that spins down, the moon then gets further away. So it's complete coincidence that we happen to be around when the moon is at roughly the right distance to cause a full total solar eclipse of the sun. But we don't always get a full total solar eclipse either, because the moon's orbit isn't a perfect circle. It's sort of an oval shape. So sometimes it's closer to us and sometimes it's further away. So sometimes you actually get these eclipses where you have this ring of the sun's light around the outside as well. So complete coincidence. And if this character here, this, Samuel Tally from Game of Thrones character, if he was, as into science as they've portrayed him so far throughout the film, he would know that, right? And he wouldn't be so oddly sort of fixated, like a weird conspiracy theorist sort of on this idea of it being 400 times closer, but yet 400 times smaller, right? He would know that it was a coincidence.
The impact made the moon ring like a bell. Bong! It rang for hours. And you know why? Because the damn moon is hollow.
Well, here's a sentence I didn't think I'd say today. The moon is not hollow. We know the mass of the moon, we know the size of the moon, and we know the density. And we know from that density that it cannot possibly be hollow. We even left seismometers on the surface, right, to detect moonquakes, like earthquakes, but on the moon. And we worked out the majority of the mass is, in the core of the moon, but that's the same way that the Earth is set up as well, with the majority of its mass concentrated in the center in a big iron core that's very, very dense. It's the fact that the moon and the Earth are actually made from similar materials that we know that this giant impact is what formed the moon, because everything then coalesced from the very same materials as it was all thrown out in that big impact. So no, the moon is not hollow.
Look at the data. A natural body does not change its orbit overnight. Yeah.
Well, I mean, yeah, he's right. A natural body does not change its orbit overnight unless there's something catastrophic happen to it. So if you did want to change the orbit of the moon, I mean, not you or me, right? But if the universe did want to change the orbit of the moon, there's two ways that could possibly happen. Either you could have an incredibly large impact, or you could have a very fast impact. Essentially, both those would give the moon enough energy, or at least in the impact, they would exchange enough energy to change the moon's angular momentum, to change its energy in order to change its orbit completely. With a large impact, you're talking a body bigger than the moon, but all bodies bigger than the moon in the solar system are already in orbit around either the sun or Jupiter or something like that, right? They're never gonna also remove themselves from those orbits in order to be able to impact with the moon. And then if you're thinking about, well, a very fast impact, that's also incredibly unlikely because the things in the solar system that will be moving that fast to have such a huge amount of energy when they impacted with the moon will have already essentially left the solar system. They will have been completely unstable objects that wouldn't have been able to get into a nice orbit around the sun. They would have been essentially slingshotted out of the solar system to become like rogue interstellar objects, just, you know, in the depths of space, just completely isolated. You also could have an interstellar object that would enter the solar system, the likes of Oumuamua, that came through the solar system a couple of years back. But again, like the odds of that actually impacting with the moon and having enough velocity to exchange enough energy to change the moon's orbit to that degree are very, very unlikely. Fun fact though, related to disaster movies, this is the way that we would change an asteroid's orbit if there was one on a collision course with Earth. We would essentially take something fairly heavy and crash it into an asteroid at high speed in order to exchange enough energy to change that asteroid's orbits that either, you know, took a little bit longer to get to the Earth, in which case the Earth would be past where the impact was going to happen, or it would, you know, get to the Earth a little bit quicker, in which case the Earth would be a little bit behind in its orbit again and it would miss the Earth. And NASA is currently testing that plan with the DART mission that's set to arrive at an asteroid in September 2022.
Can someone tell me what the hell I'm looking at?
The moon has entered an elliptical orbit.
Again, moon is already on an elliptical orbit. I guess what they mean is that the ellipticity of that orbit, so sort of like how non-circular, how sort of elongated it is gotten more elongated, I think is what they're probably trying to say.
Meaning?
It'll circle around us 3 times before it reaches the Roche limit at 17,000 kilometers.
Okay, so a couple of things. They said it'll circle around them 3 times before it hits the Roche limit. If the moon, for whatever reason, was actually coming towards us on its orbit, it would take, you know, a lot longer than 3 orbits for it to decay that amount and actually reach the Earth. The Roche limit is a real thing in science. The Roche limit is essentially if you've got 2 bodies, so let's say the Earth and the moon, and they get to a certain distance away from each other, which is the Roche limit. That would be the point at which the tidal forces on the smaller body, the moon, would be so much stronger than the force of gravity holding it together that the moon would essentially get torn apart. So what I mean by tidal forces essentially is the difference in gravity on one side of the moon to the other side of the moon. Just because it's so much closer to the Earth, that would be so much stronger over here than this side, that is what would cause that sort of shear force to tear the moon apart. And essentially what would happen when it hit that Roche limit, if it was coming in incredibly slowly, obviously, like it would in reality if this was to happen, is that the moon would essentially become a ring system and the Earth would look more like Saturn than it, you know, it does in terms of the Earth and just the solid moon orbiting us. And the Roche limit isn't like a set limit around the Earth that's the same for every single object coming in. It actually depends on the density of both the Earth and whatever other object is on its way in as well. That's why around Saturn you actually get moons orbiting within the rings of Saturn as well, because, you know, they're still held together by their own gravity, whereas the rings, which are much less dense, are torn apart by the tidal forces much sooner than that. What did he actually say? Did he say that the Roche limit was?
Meaning?
It'll circle around us 3 times before it reaches the Roche limit at 17,000 kilometers.
See, he said 17,000 kilometers. That sounds a bit pretty big for me. We could actually work it out, you know. There's an equation for the Roche limit. Let's work this out.
12 seconds later.
Okay, so the equation for the Roche limit depends on the radius of the moon, the mass of the Earth, and the mass of the moon, because it really depends on density, but all those things cancel out. So let's plug in some numbers. So the radius of the moon is 1,737.4 kilometers. The mass of Earth is 5.972 times 10 to the 24 kilograms. And the mass of the moon is 7.342 times 10 to the 22 kilograms. If you plug all those numbers in, you actually get 9,484 kilometers, which is around about 1.5 times the Earth radius. So, 9,484, not 17,000. Just saying. Probably should have done the maths. So I think this must be the start of sort of, you know, all of the chaos and destruction that's going to happen because the moon's getting ever closer. So this will be much higher tides than we're ever used to, you know, coming further and further inland. Tides caused by tidal forces, like I was talking about before, right? The pull of the moon makes it so that you have a bulge in the Earth's oceans pointing towards the moon all the time, right? So that changes as the moon orbits around us and changes its phase. So when the moon is in its full moon phase, it's directly overhead at midnight. That's when it's pulling on the oceans and you get a high tide at midnight. But when it's in its half moon phase, it's either directly overhead at sunrise if it's waning or sunset if it's waxing. And so therefore you only get the high tides at sunrise and sunset. And so when we look at this clip and we've got a half moon and it's clearly not sunset or sunrise, it's clearly at moonrise, this whole picture just doesn't make sense. It's also worth pointing out here that, like, it won't just be the oceans that will experience tidal forces as the moon gets ever closer and closer to Earth. Like, you'll also get the actual very crust of the Earth affected by tidal forces, in the fact that, you know, that will also be pulled slightly towards the moon as well. And then you'll start to get more earthquakes, more volcanic eruptions, as well as literally, like, the moon uses the Earth as like a little squishy ball.
I've got a big-ass gravity wave coming your way. You have to launch now. Over.
Did he say gravity wave?
So I think what's going on here is that they said they were going to launch when the moon was directly above them, because that would help them launch only on 2 engines, because they would be attracted more to the moon's gravity and it would help them out. And so I think what's happening is that the idea is, like, the moon is directly above them and therefore the very oceans themselves are being attracted to the moon up off the Earth, but they're describing it as a gravity wave. And that's just complete nonsense, right? So a gravitational wave is a wave that stretches and squashes space itself. It's sort of like the energy from a big cataclysmic, like, explosion or merger or something incredibly, incredibly heavy that then sends this ripple out into space. And what it does is cause this change in distance between objects as this wave passes through. Sort of in the way that we would describe gravity under Einstein's theory of general relativity, of being mass curves space and time itself. And if you remove that mass or make it heavier or make it move in some way, you will send out these ripples out into space. But, I mean, the kind that, you know, for example, LIGO or Virgo detect, these gravitational wave detectors that detect the gravitational waves that come from the merger of 2 black holes or a black hole and a neutron star, right? They are waves that, you know, are smaller than an atom itself, right, in terms of the magnitude that they're detecting. So gravitational waves are a tiny, tiny thing. As I said, you would never, ever describe this as a gravity wave. It doesn't make any sense.
Come on, let's go. Let's go.
Like, I feel like they're really hamming up this whole, like, when the moon is, like, rising or above you, that's when, like, gravity starts to get stronger and you start to get pulled towards the moon. But, like, if the gravitational effect was that strong, like, that would be happening, like, wherever the moon was in the sky, whether it was rising above you, setting, or even, like, you know, on the other side of the planet. You would be pulled with that same force to the surface of the Earth, even when the moon was on the other side of the planet, right? Especially if it was that strong as to pull small children off the ground when it starts to rise.
Oh, God. That's a white dwarf.
White dwarf. I'm sorry, I'm still processing the fact that there's a white dwarf inside the moon. So, I mean, a white dwarf is what's going to happen to the sun when it runs out of fuel and dies, essentially. You know, there's no hydrogen left to burn into helium. Shed all of its outer layers into space once it's become a red giant. And it'll leave behind this inert helium core that would be incredibly, incredibly hot. So it would be glowing and everything from gamma rays and X-rays and all this harmful radiation that you would not want to be that close to. And also, you wouldn't be able to look at it. You'd be absolutely blinded by it as well. You wouldn't be like, whoa, a white dwarf. You'd be like, Jesus Christ. And white dwarfs are anywhere from like 10% of the mass of the sun up to 1.44 times the mass of the sun, which is known as the Chandrasekhar limit. It's the maximum mass you can actually have in a white dwarf. Essentially, if you add more material onto it at that point, it wouldn't be able to hold itself up anymore and it would collapse under gravity down into a neutron star. And then a similar process would happen to a neutron star, and about 3-ish times the mass of the sun, it would become a black hole. So you've got something that's around about the mass of the sun anyway. And yeah, okay, white dwarfs are incredibly dense. They're around about, you know, like 1% or so of the sun's radius, you know, in terms of that much mass, but condensed into that small of a space. But I still think that would be small enough to fit inside the moon. And the thing is also, like, as a white dwarf gets heavier, its radius gets smaller as well. So to fit it inside the moon, it'd have to be an even heavier white dwarf. And I guess that would explain why they were like, oh, our gravitational calculations are all off because we haven't got the mass of the moon right. But you're able to measure the mass of the moon, the gravitational forces, the way we measure it, it's through its effect of gravity. So we would always have been able to get at that mass and know there was a white dwarf inside it. But anyway, I mean, we could actually work this out, like we did with the Roche limit before, because there is a relationship. I think the radius of a white dwarf is inversely proportional to its mass to the power of a third? I think let's look this up.
1 minute, 37 seconds later.
Okay, yeah, so I was right. So the radius of a white dwarf is inversely proportional to the mass to the power of a third. So, okay, let's just take a known white dwarf. So Sirius, the dog star, for example, is a normal star with a white dwarf around it. And so because the two are orbiting each other, we know their masses quite well. So let's use Sirius B as our white dwarf to work out the proportionality too. So, also looking this up, so Sirius B, once it loads, is how much of a mass is it? So Sirius B is 1.018 times the mass of the sun in a radius of 0.0084 times the radius of the sun. Okay, so let's figure this out. Okay, so we want to know the mass of a white dwarf that would fit inside the moon's radius, and I'm expecting it's not going to. So let's go with the entire moon radius rather than what looked to be like a small fraction of it, like here. But that would mean that the radius of the moon divided by the radius of Sirius B would be equal to the mass of Sirius B divided by the mass of our white dwarf inside of the moon, all to the power of a third. And so if we rearrange this with the mass of our white dwarf moon, we get that that'll be the radius of the moon divided by the radius of Sirius B cubed all times by the mass of Sirius B. And so if we look at those numbers, we find that the mass of the white dwarf inside the moon would have to be 38.77 times the mass of the sun, which is bigger than the Chandrasekhar limit, right? That maximum mass that is allowed for a white dwarf. So it's physically impossible to have a white dwarf that would fit inside the moon. So I guess Roland Emmerich just decided to ignore basic physics of electron degeneracy, pressure, and the Pauli exclusion principle for the sake of the plot here.
I knew it.
They've harnessed the building blocks of the universe!
No one look at me. I might cry.
I love the fact that John Bradley is from Manchester because it makes him sound so much like Brian Cox there. It's ridiculous.
And the universe.
No. Ugh. Watch the Hubble Space Telescope get destroyed in so many sci-fi films. Like, they did it in Gravity as well. I don't want to keep watching the Hubble Space Telescope get destroyed. Please.
The moon's entered the atmosphere over the North Atlantic.
Yeah, also, like, remember the Roche limit that they were talking about before? How we calculated it was like 9,000 kilometers away from the center of the Earth. It was like 1.5 Earth radii. The moon would break apart completely and become rings. Would never actually enter the Earth's atmosphere. Remember that? I mean, that really is the last of the problems. We've got some sort of weird, like, nanoparticle swarm thing going on here anyway. We're really in, like, Marvel territory now.
We saved the Earth.
We should get started.
Get started with what?
Alright. I think that's enough torture for one day. No, I'm joking, honestly. If you love cheesy disaster films, you're gonna love this film, right? In terms of the science, There was a little bit that they got right, but that was far outweighed by the amount of science they just ignored for the sake of plot, right? This was the sci-fi that was definitely firmly rooted in the fiction side of things. If there are any other TV shows or films in the sci-fi genre that you want me to react to as an astrophysicist, let me know down in the comments below or over on social media. I've also been thinking about ranking recent sci-fi films in terms of scientific accuracy, so let me know if that's something that you'd be interested in seeing as well. I'll be back next week for my latest episode of Night Sky News, where we recap all of the latest space news and what you can see in the night sky in the next coming weeks as well. But until then, everybody, happy stargazing. Before we get to the bloopers, I just want to say a big thank you to Brilliant for sponsoring this week's video. Brilliant is an interactive STEM learning website and app that helps you to learn new concepts across topics in science, maths, and computer science. I've always found that I learn best by doing and getting really stuck into a topic. And Brilliant's hands-on courses let you do just that at your own pace in a really intuitive and fun way. Now, in the film Moonfall, the alien villain ended up being a corrupt, artificial, intelligent nanoswarm. But if you've always been curious about machine learning and artificial intelligence, check out Brilliant's course on neural networks, with the real science on how we teach machines to teach themselves. Neural networks are a tool we also use in astrophysics to help classify the reams of astronomical data we have, but they're applicable to so many problems, so it's a great knowledge base and skill set to have. So if that sounds like something you'd be interested in, head to brilliant.org/Dr. Becky, or you can click on the link in the video description down below and sign up completely for free. Plus, the first 200 people that go to that link will get 20% off an annual premium subscription. So thank you so much to Brilliant for sponsoring this video. And now, roll those bloopers.
Process. Thankfully, our friends at SpaceX have a propellant depot currently in orbit.
I love Elon.
That's the third reference to Elon Musk or SpaceX in this film. Am I 50 minutes in? Is it sponsored by SpaceX or something? Or is this just to appease all of the Elon Musk fanboys that are watching? I got hungry or bored. I'm not sure which. I got snacks.
Brian, what's the plan?
Save the moon, save Earth. Casey was right. A what?
Save the moon, save Earth. Do you think one of the writers watched Heroes during lockdown? Save the cheerleader, save the world. It's just too similar.